Welcome to Differential Equations. This is section 3.7, and we're going to do activity 371 today. So in this activity, we have a harmonic oscillator with varying spring constant, which means we kind of imagine it as if we have a system where we know the mass and we know the damping, so for instance, the type of fluid or the type of resistance we would get from the spring, and we're trying to figure out how strong the spring to make it. So by having the unknown, the spring constant be unknown, kind of testing out like, well, what would happen if we had a weak spring? What would happen if we had a strong spring? And figuring that out. And that's really what this section is all about. It's all about using this idea of the trace and the determinant to get a big picture idea of what's going on. And so that's what we're going to do. So we have mass times x double prime plus the damping coefficient times x prime plus the spring constant times x equals 0. And we're given that mass equals 2 and the damping coefficient is 2. We just haven't picked out what spring we like. So first, we're going to rewrite it as a first order differential equation. So if I write y equals x prime, then I can rewrite this as m y prime plus by plus k x equals 0, and solve for y prime. Y prime equals negative b over y m times y plus, let me just rewrite that. Y prime equals, normally we write the x term first, negative k over m x plus negative b over m y. Okay, so then our system is x prime equals 0x plus 1 times y, and y prime equals negative k over m x plus negative b over m y. So that means our matrix, our coefficient matrix, is 0, 1, negative k over m, negative b over m. Okay, so the trace and determinant of our coefficient matrix. So trace is adding up the diagonals, so that's negative b over m, which is, I guess I should use the fact that m and b are both 2, so it's really negative 1. I should rewrite a with our actual numbers, 0, 1, negative 1, and then, nope, don't know k, sorry, negative k over 2, and then negative 1. Okay. So that means our trace is negative 1, and our determinant, that's equal to that minus that. So 0 minus k over 2, so minus negative, so that makes it positive k over 2. Okay. Then sketch a line in the trace determinant plane that parameterizes the family of equations. So I'm going to switch over to Desmos to do that. Okay, so now I'm in Desmos, and I am, I've graphed, so we're graphing the trace determinant plane. So we graph trace on the x-axis and determinant on the y-axis. And then we have this line of trace squared equals 4d. So then that's that line. So x squared equals 4y, otherwise known as y equals x squared over 4. And so then in this, the book already kind of goes over what it looks like depending on like where you are in this. And because coefficients of drag and spring constants can only be positive, that makes our trace has to be negative and the determinant has to be positive. So we're in this quadrant. That's really the only way to be. So if we're on this line, that means it's an undamped spring. So that's like a spring in one of those physics problems that can't happen in real life, where there's no coefficient of friction. So this line right here, those have been most of the physics problems you do before differential equations. Then these sections over here are more realistic versions. So you could have underdamped, where this is an underdamped spring will go back and forth and eventually settle. And then an overdamped spring will just go kind of like a screen door, just like then slowly. And then critically damped is just like that, perfect kind of like really smooth movement. So off the top of my head, I don't know exactly what critically damped would look like, but I could model it and then tell you. So here, what we're going to graph is the fact that our trace was -1. So that means trace is the xy, so it's going to be here. So trace is stuck at -1. And then determinant's going to be k/2. So determinant can be from, k goes from 0 to infinity. So determinant can be 0 all the way up to infinity. So we can graph that using, we can graph the line of possible values using -1 in the x, and then t/2. So t would be, your k value. Then you can put in Desmos, you can put in with your k there, and let k be a slider. And so then I could do that, and I can see, okay, so when spring is really weak over here, so this is a small k, so a really weak spring, the spring will act in overdamped fashion. And as soon as I get k to be, that's, I believe, one quarter. So as soon as k is like 1/4 or 1/2, sorry, as soon as k is 1/2, then you're at critically damped. And once k is more than 1/2, then the spring is going to go back and forth. Okay? Which is something really worth knowing in that situation. If you're building something with a spring and you want it to actually like move back and forth and not just like slowly move towards where it's going, then you need this sort of scenario is how you kind of determine how strong the spring you want it. And so then let's see what the next question is. What values of k is a harmonic oscillator underdamped, overdamped? What value do you have a bifurcation? So overdamped from 0 to 1/2, and then underdamped from 1/2 to infinity, and there's a bifurcation at 0.5. Okay, so that is this activity.